Now we're going to move on to case number 3. This is a case where the denominator is going to contain not a linear factor, but an irreducible quadratic factor. Now, it's important to note that this quadratic factor that exists down there, again, while irreducible, is also not repeated. So this would mean that if ax squared plus bx plus c, that's a quadratic, if this is an irreducible factor of the denominator, then what fractions can I create from this? Well, what we can really say is then the partial fraction corresponding to this factor is going to just be a single fraction with my denominator ax squared plus bx plus c. And in the numerator, in order to keep this a proper rational expression, I'll have to make the power up here, or the degree up here, 1 or 2 lower. That is, just got to be something smaller than what I see in the denominator. So that would allow me to possibly have something linear up top with power 1, or a constant. And since I'm not sure which, I'll go ahead and write this as something linear. But if I find in the process of solving that a is a 0, then I know that I'll just end up with something that is a constant in the numerator. Now again, this can seem a little bit weird at first, but let's take a look down here at example 4 to see how this plays out. We'll start in the same way that we always do. We'll note that we have a proper rational expression, and so we'll start to search for the partial fractions. And to do that, we're going to go ahead and make sure that we fully factor our denominator. So here I'll notice that I can factor out an x and an x squared plus a 1. Now, can I factor x squared plus 1 anymore over the real numbers? And no, I can't. That is irreducible, can't be factored anymore, and it's certainly quadratic. Notice though, I also have here a distinct linear factor. So I know that I'll have to tackle this with a combination of case 1 and case 3. X is going to receive its own fraction, and my irreducible quadratic is going to receive its own fraction. Up above, I'll put bx plus c. Again, it may or may not end linear. It kind of depends up there as to whether or not the value of b is 0 or not 0. But this is the general shape that I would have. And the rest of the approach is very similar. I'll start by getting a common denominator between these. I want to make sure that the denominator that I create is going to match perfectly the denominator that I started with. And so you can see what I have over here matches over there. And so if these two fractions are going to be equal and their denominators already match, then that means that we need a 4x squared plus a 2 to be equal to an a times an x squared plus 1 plus a bx plus c times an x. Now, here we're going to see something a little bit interesting. I would ask you to not write this down yet on your own paper, but think through this here really quickly. In the last questions, what we've often done is we've started to kind of select certain values for x. Now here, maybe the easiest value to select for x might be something like a 0, because I can see it'll actually completely eliminate all b's and c's from what I have here. So if x was equal to a 0, then notice I'm really just going to get 2 is equal to 1a over here, and boom, I would have immediately found a value of a. But notice that after this is done, are there any other easy values of x that I could choose to maybe like cancel out, the a's, or cancel out the b's, or just the c's? what you'll see is that over here, there's not really much more I can work with. And actually, since x squared plus 1 is irreducible, that means there are no numbers I can plug into it that allow me to actually generate or to turn this factor here into 0. So what I'm going to do here is take a slightly different approach when I start to involve case 3 or later case 4. Instead of taking this approach of plugging in values for x, I'm going to go ahead and quickly see what happens if I rewrite the other side of my equal sign here. To do this, I'm going to just distribute my value of a and my value of x. Notice that if I do this, I'm going to get ax squared plus a plus bx squared plus cx. And I'm going to rewrite this one more time. Notice I can see here that I have a plus b x squareds. Right? I have a of them over here, b of them over there. I have c x's, and I kind of have a constant of a. Now this is again a new way of thinking about finding the values of a and b, but hopefully it should still make sense. If these two sides are supposed to be equal, don't they have to have the same number of x squareds? Don't they have to have the same number of x's? Don't they have to have the same constant at the back? Well, if that's the case, then what I can see is that 4 is definitely going to have to be equal to a plus b, right? I need 4x squareds. That's got to be 4x squareds. I can see that, well, I have 0 x's on the left side. That's got to match up with c. And if 2 is sitting over there on the other side as a constant, that's got to match up with a. And what I generate here is actually a system of equations. Now this system is so easy that I've already solved for 2 of the values. And of course, once I've solved for those 2, it's pretty easy to find the remaining. You might be able to see here that if a is a 2, that means that b is also going to have to be the value of 2. So once I have this, I found all my values rather quickly, and I can go ahead and finish the question. So my integral, 4x squared plus 2 over x cubed plus x, that's going to be equal to an integral of, and again, I'll write a over x, so 2 over x, plus 2x plus 0 over my x squared plus 1. So it's kind of interesting here. The c ended up being a 0. It's ultimately just going to disappear. No big deal. If I was to separate this out into 2 integrals, notice that's 2 over x dx, and then 2x over an x squared plus a 1. Now the first integral here is actually rather simple. I know I'm just going to get 2 natural log absolute value of x. But notice that again, when these quadratic factors start popping in here, my new resulting integrals are a little bit more complicated. I have to think a little more carefully about this. Now, there's 2 ways you could attempt to try to tackle this. You could guess and check, but you might also be able to see that, couldn't you do a nice simple u sub here? You could select u to be an x squared plus a 1, and then du, which is 2x dx, is actually already sitting there. So notice that this is all going to turn into a natural log, 2 times a natural log of absolute value of x plus an integral of, let's see, this would be 1 over u du, or 2 natural log absolute value of x plus natural log absolute value of x squared plus 1, all plus c. This is the final result I end up with. Again, it's important to note that our new case here really didn't add that much. It just told us how to create this quadratic factor fraction, that I would take that irreducible quadratic, position it in the denominator, and just put a potential something linear in the numerator. In the next video, we'll take a look at example number 4, case number 4. But before you go ahead and watch that one, I would highly encourage you to try to work through some of these problems in example number 5. They can be a little bit more challenging than some of the stuff that we've seen, or fairly similar. But go ahead and give it a shot to at least see how far into this process you're really understanding.